What, sweetheart? Zillow wants me to fill out this long-ass application. She said just send her a message. So I gotta teach right now, but I'll do that. I'll finish it in a minute. All right. Good morning, guys. Sorry about that. So let's get started. I know there may be some folks here who were not here the other day. Before we get moving into this, I just want to ask that anybody who has their name in Zoom set as something different from what they have on their Santa Fe ID, please take a minute to change that. If you have to sign out and sign back in to do it, that's okay, no big deal. But it's really important that I'm able to accurately report your attendance for financial aid purposes. Your financial aid won't disperse until I mark you as having attended. And there are some folks I see here who have different names or pseudonyms or things like that. So please go ahead and change your name in Zoom to whatever it is that's on your Santa Fe ID so I can mark you as attended and you can get your financial aid dispersed. Today's going to be our first day of all mathematics, but before we get into that, I do just want to remind folks who may have missed the other day where they can go to see the introductory material from yesterday in case they missed it. Let's see, sorry about this. I'm applying to rent a house right now, but first things first, let's get this going. Normally, I'll go ahead and say also, normally I do my first activity, group activity for Mac 1105 in week 1, but because we started on a, well, no, we had a Tuesday and a Thursday. I guess I just feel bad doing something that can't be made up when there are still folks who have the ability to add the class. So because classes can be added until Monday, I'm going to hold off on that activity 1 until next Tuesday. And that'll give us some time here to talk about how we're going to do it. All righty, so let me get set up here and I will introduce the day and then we'll do a little bit of recollection from yesterday, and then we're going to dive into some math. So this, of course, is Mac 1105, College Algebra, section 007. This is a lecture, and the date is January 7th, 2021. Let me get this to focus. There we go. Oh, no. Come on. All right. I might switch to a slightly more bold color here too. Okay, so today what we're going to do oh, damn, that's not good. Today what we're going to do is quick reminder about MML, registration, syllabus stuff. And then we're going to talk about functions. We're going to talk about function types. And we're going to talk about linear functions. And slope. Because these are the things that you need for your first homework set. And I'll remind you that your first homework set opened Tuesday, day before yesterday at the end of class, and is due next Tuesday at the start of class. So those quick reminders for anybody who is not here on Tuesday, let me show you a few things very fast. If you come to the home page in Canvas for our class, that's the syllabus page, you'll see a bunch of really useful stuff like links to join the office hours and the times and days for the office hours. These are Monday, Wednesday, Friday, 1 to 2. So you click that link at those times to join that office hour. Or Tuesday, Thursday from 11 to 12. And you would click this link on those days to join that office hour. The final exam, if you did not put this in your phone's calendar already, please put this in your phone's calendar right now. It's very important that you do not forget when this is. All of the homework for this class is going to be in my math labs. So will the quizzes. And we already have stuff up there that you guys need to be working on. So I'll show you really quick what this looks like. If you haven't registered, you would click register down there. And here are the first few assignments that you guys need to be working on. So there's an algebra readiness assignment, and then you have homeworks 1, 2, 3, and quiz 1. These are all due at the start of class next Tuesday. So please get in here and start working on these immediately. Even if you don't have your access code for MyMathLab, you can get in there and start working on them. The only thing you need to get into the MML course and start working on the actual homework for the class is the course ID, which is here in the syllabus. So if you download the full syllabus, it's that PDF, you'll see this course ID. This is what you need to get registered for MyMathLab. They will also ask you for an access code. If you don't have your access code yet, either you haven't bought it or you're waiting for it to ship to you, just look on that page where they ask you for the access code for a link that says click here to start trial access, and that will get you in there for 2 weeks. So as long as you get your access code within the next 2 weeks, you can use the trial access and you won't have any problems. But please remember, to get into MML, you need to register using this course ID from the syllabus. And again, I recommend you save a copy of this syllabus somewhere safe on your computer. All right, so we have several homeworks and a quiz that you need to get started on. You need to get started on these right away. I will be going through how to solve some of these problems today. A little bit of it we've talked about already, the interval notation and how to go from an inequality to an interval and so on. But most of it we still need to talk about. So that's what we're going to be spending the bulk of the day doing. I understand that there are some questions about the homework, and I will certainly be addressing those. But before we get to that, are there any questions about registration, MyMathLab, when is homework due, all that stuff? Remember, you can hold down the space bar to talk, or you can type in the chat. I'll always have the chat window open and be watching that. Watch out, though. Watch out, big guy. Yes, you're very sweet, but you're going to get hurt if you stay there. Okay, so it seems like most of us are pretty comfortable getting into MML. Again, if you do have any trouble with that, please just send me a message on Canvas or send me an email. If you do email me, please put the course name, College Algebra, in your subject so I know what you're talking about. Let's get into the material. Kendra asks a really good question. Is there any way to access the notes from Tuesday's class? If you missed Tuesday's class, thank you for asking that, Kendra. Come back here to the announcements where we found the link to join the class, and you'll see that I've updated the announcement from Tuesday. Instead of just saying link to live lecture 1.5.21, it now says link to live lecture 1.5.21, updated with link to recording. If you come in here, click this link, you can watch the full lecture from Tuesday's class. Now, I don't have the notes scanned or anything like that, but you can get all the information from any class through this mechanism, and I'll always do that. I always record the lectures, and I always upload them to YouTube after the fact. Reminder, in case you didn't hear me say this on Tuesday, this is not a replacement for coming to class. I do take attendance. There is an attendance component to the grade, and if you just get in the habit of watching these lectures instead of actually coming to class, you will lose points from the attendance. So please continue to come to class even though these are online. Alrighty, so coming back here, I want to spend a little bit of time just going over these things in general before I take specific questions from the homework, but I will pay attention to time. And when we get down to like 15, 20 minutes of class left, I will shift from lecturing to taking any questions you want from the homework. My cat is a terrorist. He wants back in. Come on, bud. All right, you gotta stay though. Alrighty. So what is a function? We've encountered functions at a bunch of different places in our past, certainly in high school and probably in other previous math classes. What is a function? A function is a relation mathematicians call these things relations, but a relation is just a rule. So a function is a relation or rule for pairing inputs with outputs. Right? It's really just that simple. Another quick reminder, anything I write on the document camera here goes into your notes. Okay, you guys need to be transcribing everything that I write down here into the notes. So a function is a relation or a rule for pairing inputs with outputs. And for us, both the inputs and the outputs will be numbers, right? So it's a rule for pairing numbers with other numbers. The way we normally write this is f of some input is equal to some output. F is the function, or the name of the function. The input will usually represent by the variable x. And the output will often be given as a formula. Not always, but often. As a formula in terms of x. All right, this is how we're usually going to encounter functions. And most of the time in previous math classes, when you see something like this, f of x equals 5 minus x or something like that, you know, it looks like this, f of x, right? F of some input, the input is x, equals some output. And usually that's some formula that involves the variable x. And oftentimes we'll use the variable y to represent that output as a single thing. But this is not the only way to do that. There's other ways to come up with rules or relations that pair inputs with outputs. So there's really 4 ways to describe a function. We call them representations. All right, and I want to use the exact language that's used in your homework. We'll grab that. So the first and most common way is the one that I've just given you here, right? It's a symbolic or algebraic representation. And an example of that, and remember I'll use the letters E.g. to tell you I'm writing down an example. An example of a symbolic or algebraic representation of a function might be something like f of x equals 5 minus 1/2 x. We call it symbolic or algebraic because there's an algebraic formula that tells you the output in terms of the input variable. So this would be the function named f. I could have named it g or h or anything else. It tells you that the input variable is x, and these parentheses here, this is not f times x, that's f of x. You can kind of think of f as a little monster and these parentheses as being its mouth. It eats the x's and it poops out these things. These things are determined by the input, right? You feed this thing a specific number x, and it poops out 5 minus 1/2 times whatever the x was that you fed it. Another way to represent a function is as a table. We call that tabular or sometimes numeric. Right? So I give you an explicit table, a list of inputs and outputs. And the inputs and outputs are arranged so that you can tell which output comes from which input. So usually that will look something like this. The table may be oriented vertically, it may be oriented horizontally, like I'm doing here. So maybe I've got the following inputs, 0, 1, 2, and 3. And associated with the input 0, maybe I have the output 5. Associated with the input 1, maybe I have the output 9/2. Associated with the input 2, maybe I have the output 4. And associated with the input 3, maybe I have the output 7/2. Okay, and sometimes these will be oriented like I'm showing here horizontally, but sometimes this table will be turned vertically also. So up here in the row that has the x in it, these are all inputs. And down here in the row that has f of x in it, these are all the outputs. So if I feed this function the input 0, it spits out the output 5. If I feed this function the input 1, it spits out the output 9/2. If I feed it the input 2, it spits out the output 4. And if I feed it the input 3, it spits out the output 7/2. So this is another way of representing a function as a table, where I just explicitly tell you, here's all the inputs, here's all the outputs. And we arrange them so that you can tell which output comes from which input. Everything good so far? Okay, I see some thumbs up. Beautiful. All right. Another way I can represent a function is verbally, or linguistically, if you want. This is where I tell you what the function does using words. So remember, a function pairs every input to an output. That's what functions do. They take an input and they fart out an output. If I tell you how to get the output from any given input, that's really the same thing as doing this, right? This is a formula that tells you how to get the output from any given input. I can do that with words instead of with algebra formulas. So for example, I could say f is the function which takes the input x multiplies by 1/2 multiplies x by 1/2, then subtracts that result from 5. And you may or may not have noticed that the first two functions I gave you, or the first two examples I gave you there, actually represent the same function or the same operation. This is a verbal description of the function here, right? If you want to compute an output from this very first example, given an input, you would take that thing, right? You just plug x into this formula, which means you'd take x, multiply by 1/2, and then subtract all of that away from 5. Well, that's the same thing here, just described in language rather than explicitly given as an algebra formula. Let's said I wanted to use the exact language that's used in your homework, but I don't appear to have your homework printed right here. I had it yesterday. So let me check one thing really quickly. I just want to make sure I'm being totally consistent. I think it's right here. And they use a certain sort of language. I want to make sure I use the exact same language. Symbolic. Where's this? Give me just 1 second. I actually really want to find this printout I have of your homework, so I'm using precisely the same language that they do. I will be just 1 second to find this. Here, let's turn this off for a second. I'll just print a fresh copy. Okay. Well, I'll just leave this up. This is fine. Okay, so they call it symbolic, numerical, verbal, and graphical. That's what they call it. Okay, so our last way of representing a function here, the terminology that's used in the textbook is graphical. And this is what it sounds like. It's where you can infer the function rule from a graph. So I'm going to move the page up just a little bit here. Last way we can represent a function is graphically. This is where, rather than giving you an algebra formula, a table, or some words, I give you a graph of input-output pairs. So let's see. All right, and rather than labeling all of these, I'm just going to label some of them.
We can't see the screen.
Oh, I'm so sorry. Here, let me turn my screen share back on. I turned it off to print for a second. Thank you, thank you. All right. Here we go. So I'll leave this just for a second in case anybody's still writing, then I'm going to move the page up a little bit. So our 4 ways of representing a function: symbolic or algebraic, tabular or numeric, and verbally or linguistically. Examples of each. So a symbolic or algebraic representation of a function is where I give you a formula. Tabular or numeric representation is where there's a table. The numbers are just explicitly given as input-output pairs. Verbal or linguistic is where I tell you in language, right, in regular English language, what the function does to inputs to get the output. And then this last one, graphical representation of a function, is where I give you a graph of inputs and outputs. So the horizontal axis here, we should all be somewhat familiar with this. We usually label as the x-axis, and the vertical axis we usually label as the y or f of x axis. And the idea is that any ordered pair along this line is of a special form. It's of the form x comma f of x, meaning that the y value at this point is the output associated with the x value at this point. Does that make sense? So the y value at a point on the graph is the output associated with the x value at that point. So the graph is made up of all the ordered pairs of the form input, comma, output. Now, in all four of these examples, I'm describing the same function, or the function I'm describing has the same behavior. It's a linear function, and we're going to look in more detail at that. But you see here, for example, in this table, I have the input-output pair 0 and 5. The input 0 goes to the output 5. And if you look on my graph over here, I have the ordered pair 0, comma 5. That's this y-intercept. When x is 0, f of x is 5. In other words, f of 0 is 5. So the point 0, comma 5 is on the graph. If I were to come over here to 2, this point right here is 2, comma 4. So the input 2 is sent to the output 4. Or in other words, f of 2 equals 4. An important note here is this: if the point a comma b is on the graph of f of x, that means f of a is equal to b. Now I'm going to go ahead and move this up. Here we go. I'll give you guys a second to get all these little bits down. I apologize for the little break in continuity there. So our last way of representing a function is graphically. The horizontal axis is the input axis, meaning any number down here for which there is a point above is an input for the function. And the vertical axis is the collection of outputs, meaning any value over here for which there is a point on the graph is an output for the function. And I'm graphing here the same function that we used in the previous three examples. It's that linear function whose slope is -1/2 and whose y-intercept is the point 0, comma 5. Any questions on this concept, these four different ways we can represent a function? Yeah, I see something here in chat. No? Okay, cool. Okay, should we have ordered pairs? Oh, I see. There's a quick question from Mark there about the homework. How do you enter ordered pairs? Ordered pairs would be entered as like an open parentheses, some number, then a comma, then a closed parentheses, the same way we would type an open interval. If you have specific questions like that about how to enter things, we can talk about those either at the end of class or in office hours. But yeah, if you're having any trouble getting MML to take answers from you, formatting wise, I'd be happy to help you with that after class. So for now, I want to move a little bit beyond this one, talk a little bit more carefully about functions. So what makes functions different from arbitrary or other rules or relations? Right? Earlier we said a function is a rule for pairing inputs with outputs, which is absolutely true. But they're a special kind of rule for pairing inputs and outputs. And the answer to this question is that a function will always send one input to one output. In other words, functions never send one input to two different outputs. This is what makes functions functions. This is really the specific part of the definition that we need to be careful about when somebody asks you, is this relation a function? So for example, it is not possible for a function f of x to satisfy both f of 1 equals 3 and f of 1 equals 4. Because here the input, this statement says the input 1 gets sent to the output 3, and this statement so it's not possible for a function to satisfy both f of 1 equals 3 and f of 1 equals 4, because this statement says that the input 1 is sent by f of x to the output 3, and this one would say that the input 1 gets sent to the output 4. And that violates this observation up here. So when you're trying to figure out whether a given relation is or is not a function, the thing you need to check is whether it's true that that function sends each input to one and only one output. Something like this, where the input 1 gets sent to 3 and the input 1 gets sent to 4, is not allowed. That violates the definition of a function. There's a few ways to detect this. I'll show you an example in the tabular settings. So let's ask this question. Which of the following tables represents a function? And here, rather than using f of x for the outputs, I'll use y's. So I'll have x and y, because we don't know a priori, we don't know ahead of time whether these are or are not functions. I don't want to use the function notation. So for my inputs here, I'll say I have -1, 0, 1/2, and 3. And for my outputs, let's say I have 0, 2, -2, and 4. And then in my other guy, I have -1, 0, -1, and 1/5. And for the outputs, I'll say I have 2, -5, 6, and 3. Okay, I'll call this relation A, and I'll call this relation B. In both cases, I'm thinking of the x's as the inputs and the y's as the outputs. So here, x's inputs, y's outputs. One of these is a function. One of them is not a function. Which one is a function? Or what is it that we should be looking for? Think about this statement up here. We have to make sure that we're sending each input to one and only one output. So which one of these is a function? Yeah, good. A. A is a function. It sends the input 1 to the output 0, sends the input 0 to the output 2, sends the input 1/2 to the output -2, and it sends the input 3 to the output 4. Every input goes to one and only one output. Careful, Mark. 1-to-1 actually means something else. 1-to-1 is kind of a two-directional version of what we're talking about. So let me get through this example, and then I'll try to clarify on your question a little bit. Kendra made a great observation in chat. The problem in B is that the input -1 is being sent to 2 in this column, and the input -1 is being sent to 6 in this column. So the input -1 is being sent to two different outputs. That violates the definition of a function, right? We cannot have one input going to two different outputs. Mark made a really neat comment in chat too about a 1-to-1 relationship, and that's not quite what we're looking at. So let me give you a couple more examples here. Same thing. I'm going to give you a table of x's and y's, and we're thinking of the x's as the inputs and the y's as the outputs. Alrighty, and let's swap these around. So Mark, I think this example will illustrate kind of exactly what you were asking about. I have the same question here. Which of the following, which table represents y as a function of x? And this language right here, you're going to see in the homework, represents y as a function of x, or represents L as a function of k, whatever. Just means that the first thing here, these are your outputs and these things are your inputs. So a function of blank means this is your input. One of these is a function and one of them is not. Neither of them are 1-to-1 relationships though. Which one of these is not a function? My chat window keeps disappearing. Yeah, see, this is a neat example, isn't it? Because it's kind of counterintuitive. Most folks in the chat are saying that B is not a function. can somebody, and I'd like you to hold down the space bar to talk so everybody can hear you, even if they're not watching chat. Anybody who would like to, go ahead and hold down your space bar and explain to me, why is B not a function? You're correct. All of you who said that are correct in saying that. It's all right. Don't be shy. We're all going to say things in this class. I'm going to say things that are wrong sometimes. If you happen to make a mistake, it's not something to feel bad about. But I'd love to hear just an explanation, just a few words from anybody. Brooke, Sophia, Tiana, Cassidy. I'm sorry, Tiana.
I don't know about everyone else, but I personally like to use the vertical line test. And even though we didn't graph this, I can kind of still see the graph in my head.
That's excellent. Yeah, the vertical line test is a really neat trick for determining whether something is or is not a function. And I'm totally satisfied with that answer. But because I haven't described the vertical line test just yet, I'd love to hear one or two more people's thoughts on this. So why a lot of people were correct in saying B is not a function. Just tell me whatever it is in your mind that told you that. It doesn't have to be perfectly formal or anything like that.
Um, I was just gonna say that, like what you said earlier was that there's only one output for every input, and
Beautiful.
like look at the table for B, you can see that there's multiple outputs for all of the same input.
Very good. Yeah, the input 5 is being sent to -1. The input 5 is being sent to 0. That alone breaks the rule, right? That alone violates the definition because the input 5 is not allowed to be sent to multiple different outputs. The function A is a special kind of function. This is a function. It's called a constant function that takes all the inputs to the same output. That's okay. This is fine because there's no one input that's being sent to multiple different outputs. Let me draw the graph of these two functions so we can talk about the vertical line test. So you guys are correct. B is not a function. Because the input 5 is being sent to multiple outputs, multiple different outputs. Okay, so let's graph these. Who can tell me an ordered pair that's on the graph of the function A? And you can, again, you can hold spacebar to talk or you can type in chat, either one is fine.
-1, 5.
Yeah, very good. So let me mark here 1, 2, 3, 4, 5. And over here I'll mark -1. Here's the ordered pair -1, 5. Right, it's this point right here. Good, yeah, the ordered pair is 0, 5. That's this guy right here. The ordered pair 1, 5. That's this guy right here. The ordered pair 2, 5. And the ordered pair 3, 5 are all on this graph. So right here, that's the whole graph of the function A. It's just these ordered pairs, just these dots. The graph of the function B sorry, not function, the graph of the relation B is different. The x's are always 5, and the y's range from -1, 0, 1, 2, and 3. So the ordered pair 5, -1 is on the graph of the relation B. That's this guy. Oops, sorry. So we go over 5 and down -1. The ordered pair 5, 0 is on the graph of the relation B. That's this guy. The ordered pair 5, 1 is on there. That's this guy. 5, 2, and 5, 3. So this is a function, the top guy here, A, and this is not a function. And I missed who it was. Was it Gabriella? Somebody, I'm sorry, a minute ago was talking about the vertical line test. So the vertical line test is a neat way to tell if a relation is or is not a function based on its graph. Notice here we've got all these points and they all live on the same vertical line. If any 2 points on the graph of a relation live along the same vertical line, then that relation is automatically not a function. This is called the vertical line test. Let's say it like this. If any vertical line intersects the graph of a relation in more than 1 point, then that relation is not a function. And here on the graph of the relation B, we can clearly see that this vertical line intersects the graph in many points. In fact, this vertical line intersects the graph at every point. So B is certainly not a function, but A is a function. If you drop a vertical line anywhere, you'll see that there's only at most 1 point that lives on any vertical line here. But if you drop a vertical line here on the graph of B, you'll see that all the points live along that vertical line. And all we would need is 2 points. If there's any vertical line that touches that graph more than once, that graph is automatically not a function. Bueno? Any questions about how to tell whether a relation is or is not a function? Okay. I'll leave this for just 1 second, but then I am going to cover it. We're going to be moving on. I'll zoom out in case you guys wanted anything from the top of the page. The next thing I'm going to do is define the domain and range of a function, something you've probably heard of before. And then we're going to talk about linear functions. Is there any one part of the notes so far that you guys would like me to zoom in on or go back to? Okay. All right. Moving along. The set of all inputs, we'll zoom in here. The set of all inputs for a function is called the function's domain. Range, the set of all outputs for a function is called the function's range. Usually you can think of the domain as being all the x values that are on the graph, and usually you can think of the range as all the y values that are on the graph. So if I return to the examples from the previous page, this fellow's domain, right, here A is a function, B is not a function. So we can't even talk about domain and range for B because it's not a function. Domain and range only applies to functions. But for A, the domain would be the set for A from the previous example. The domain is the set, and when we describe a set, we put it in these curly braces, is the set -1, 0, 1, 2, and 3. And the range is the set just containing 5. And you don't have to repeat the 5. When we write sets, we don't repeat elements. Just because 5 is listed 5 times here, or 5 times here, doesn't mean we have to repeat it 5 times in the range. Later in the course, most of our domains and ranges will be intervals, right? Or combinations of intervals, specifically unions of intervals. Remember we talked last time about unions and intersections of intervals? I'd like to give you one more example of a domain and range. But first I want to make a quick comment about something Mark said a while ago about functions being one-to-one. I'm not going to tell you what a one-to-one function is yet. We'll get there much later. But Mark and anybody else who's curious about that language, the function A here would be called a 5-to-1 function because there are 5 inputs all going to the same one output. That's where that terminology comes from, right? You've got 1, 2, 3, 4, 5 guys in the inputs in the domain, and they're all being sent to the same one function, or sorry, the same one number in the range. So there's 5 of these all going to one of those. That's called a 5-to-1 relation, a 5-to-1 mapping, in this case, a 5-to-1 function. All right. One more example involving domains and ranges, and then we're going to talk about linear functions and slope. So we're going to find the domain and range for the function g of x graphed below. And here I will draw a graph of g, and then I'm going to label some things so we can tell where stuff is. How should I do this? Let's do it like this. And maybe we'll have him come below that. And then we'll turn around like this. All right, so give me just one moment. You can draw this along with me. I'm going to be labeling some things. So give me just 1 second. Call this guy height 1. Call this 2. And we'll call this up here 3. This is coming down below that, so we'll say this guy here, maybe -4. This guy here, something -2, so that would be -3 and -1. I'll say this leftmost point over here is -5. And this rightmost point over here, we'll call this +10. All right, here is my graph of the function g of x. I want to find the domain and the range. So take a minute to draw this graph and be careful that you draw it exactly as I do. I can add in some things like this to help you see exactly what height these points are at. Okay. I have a trick for this, and you may or may not like this trick. Everybody's entitled to their own way of thinking about things, but I have here a way of thinking about these things that you may like. Unfortunately, I only have one color of highlighter here, so I have to be a little bit careful. To find the domain of a function from its graph, I like to come in here and imagine I'm a big heavy machine and I'm going to squish this guy down onto the x-axis. Right? So imagine as I come in, I'm smushing the graph and smushing the graph and smushing the graph, and it all gets smushed down onto the horizontal axis, the x-axis. When I do that, when I play this smooshing game, I call it, everything gets smooshed down onto this interval of x values. Can you guys see that? Again, I want you to pretend that I'm coming in with a big, heavy hydraulic press, and I'm just going to smush this graph straight vertically until it's all smushed onto the x-axis. This point gets smooshed to here. 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 So the whole graph gets smooshed onto the interval -5 to 10. And I've drawn this with filled in circles at the ends here, meaning there is a point right here at -5, -2. There is a point right here at +10, 1. So my domain is the closed interval from -5 to +10. And my range, to find the range, we're going to play the smooshing game again, but this time we smoosh everything onto the vertical axis. So again, imagine I've got my big heavy hydraulic press. I won't talk with the Russian accent. I don't know, do people still watch the hydraulic press channel? It used to be considered pretty fun. I come in with my big heavy hydraulic press and I smoosh everything onto that vertical axis. When I do that, this point gets smooshed to here. This point gets smooshed to here. This point stays right where it is. and everybody gets smooshed. Oh, let's see. So I almost did something wrong here. This point down here gets smooshed to here. So when I play my smooshing game, when I push everything in, the whole graph gets smooshed onto this interval of y values. All right, I'll go ahead and highlight it here. So here is my range. And you have to be careful, right? The bottom point of the range doesn't always come from the left endpoint of the graph. You almost saw me make that mistake. This guy is actually what defines the lowest point of the range. So you got to pretend you smush the whole graph onto the vertical axis. And you see here that the range is -4 to 3. I'll go ahead and highlight the domain too. I'd like to do these with different colors, but I only have the one color highlighter. All right. So when you smoosh the graph onto the x-axis, that gives you your domain. When you smoosh the graph onto the y-axis, that gives you your range. Not too bad, right? Bonus round. Now let me check the chat really quick because my chat isn't showing up for whatever reason. All right, bonus. What is g of 0? Remember, the ordered pair A comma B is on the graph, means g of A equals B. So the ordered pair 0, 3 being on the graph means g of 0 equals what? Three. Yeah, very good. What is g of -5? So the point on the graph associated with the input -5 is this point right here. So g of -5 is -2. Excellent. Yeah, thank you, Sophie, Logan. Yeah, g of -5 is -2. All right, and if these first two little bonus things have been a bit confusing, I want you to pause for a second, help me with this last one. Please withhold typing your answers for just a second so everybody gets a chance to think along with us. Somebody I have not heard from yet, and I really do appreciate you guys' participation. It means a lot to me, and it really does help with everybody in the class. So if I could hear from just one more person I have not heard from yet. What is g of 10? Very good, Kendra. Yeah, thank you. G of 10 is 1. And Tana, thank you. Because the point on the graph of g of x associated with the input 10 is 10, 1. That means this y value right here is g of 10. Beautiful. All right. So that's how we read graphs of functions, and that's how we get domain and range from the graph of a function. If I give you the function explicitly as a table or numerically, then you can read off the domain and range really easily. Just write down the set of all the inputs and the set of all outputs. But if we give it to you in a graph, sometimes it's a little bit harder. The last thing we need to talk about is linear functions. And I think probably we'll need to continue this discussion a little bit into Tuesday of next week. That's okay. I will extend our homework online just a little bit, I think, if we don't get through this, but let's see. So a linear function is a function whose graph is a straight line. That's a fine way to think of it. Equivalently, that is a function which can be expressed algebraically in the form, few ways to do this. You have what's called slope-intercept form, y equals mx plus b, or you could call it f of x equals mx plus b, or another way to write this is ay plus capital Bx equals capital C. These are just different forms of linear equations or linear functions. The important thing here, and you'll usually see it like this, the important thing here is that the input variable x only ever shows up to the power of 1. One last way of writing this is y minus y0 equals m times x minus x0. This last guy here is called point slope. This one is called standard, and this one is called slope intercept. Anything which can be written in one of these forms can be rewritten in all of the other forms. So these are your kind of 3 different ways of writing a line or a linear function. The slope of a line this can be calculated from any 2 points known to be on the graph. We use the symbol m for slope. And that's why you see the symbol m showing up here and showing up here. Let me call those 2 points on the graph x0, y0, and x1, y1. The slope can then be calculated as y1 minus y0 over x1 minus x0. And it actually doesn't matter the order you subtract these in, as long as you do the same order top and bottom. So you could also, if you prefer, to write this as y0 minus y1 over x0 minus x1, that's fine too. It's the same thing. When you change the order of subtraction in the top, that makes it negative. As long as you change the order of subtraction in the bottom, also the negatives will cancel. But usually you'll see me write it like this. For example here, let's draw the picture. If if I have a function which I know to be linear, and the following points are on there, say 1, 5 is on there, and 4, 1 is on there, then I can calculate the slope of this line by taking the difference in y values and dividing by the difference in x values. That's what this is. Some people like to call this the rise over the run between those 2 points. So here, the slope between these 2 points would be, I have to label one of these as x1, y1, and one of them as x0, y0. So I'll choose this one to be x0, y0, and this one to be x1, y1. It doesn't matter how you choose those, as long as you pair the zeros with the zeros and the ones with the ones. And here, my slope would be y1 minus y0, which is 1 minus 5, divided by x1 minus x0. That's 4 minus 1. Well, 1 minus 5, we got to follow our order of operations. So upstairs, we do everything together. Downstairs, we do everything together. Then we divide. Fractions like this are grouping symbols. So you got to think of it as being in parens in the top and parens in the bottom. 1 minus 5 is negative 4. And downstairs, 4 minus 1 is 3. So the slope of this line is negative 4 over 3, or negative 4/3. One of the things we're going to have to do in this class is get comfy dealing with fractions. I know that that is poison to a lot of us, but it's something we must overcome. And I'm going to be pretty ruthless about this throughout the semester. Fractions are just so important. This is the class where we stop being afraid of fractions. So I don't want to write this as negative 1.3333333333. I want to leave that as negative 4/3. Finding the slope of a line is a really important thing. Sometimes, though, we also want to be able to find the equation of a line. And you can tell from this picture that there definitely is a linear function involved here, right? This straight line. But I can't see the y-intercept. If I knew the y-intercept, then I could write y equals mx plus b, where m is the slope and b is the y-intercept. I'm sure we all remember that. Maybe we should come back here and just add this. M is the slope. Well, here, I'll put it on another page. So finding the equation of a line, and this is where I'm going to stop today, is after this. I'll ask you to bear with me for just a few more seconds. That way we'll be able to do all of the homework for this week. Finding the equation of the line. In y equals mx plus b, m is the slope and b is the y coordinate of the y-intercept. And if it's been a while since you've seen this, the y-intercept is just the name for where the graph hits the y-axis. But if you look at the example problem I have here, we can't tell where that graph hits the y-axis. It looks like it's bigger than 5, but that's all I can say for sure. And that's nowhere near good enough for me to say what it is. Could be 6, could be 5.9, could be something else. In the point slope form, M is again the slope, and the values x0 and y0 are any point on the line. I'm going to move this up a little bit. Any point on the line. So this guy is more powerful. Point slope is your friend. You want to become friendly with it in this class. I know that everybody is familiar with this. I know that maybe not everybody is familiar with this. There's another way they write this. Sometimes in 1033, they write this as y equals m times x minus x0 plus y0. If you would rather use this expression of point slope, that's fine with me. It doesn't matter to me which form you want to use. So if I want to find the equation of the line from the example above, I already know its slope, but I don't know the y-intercept, so I can't write down y equals mx plus b. But I do know a point, x0 comma y0, 1 comma 5. So where can I do this? I'll just move it up here. The equation of the line from the previous example can be written in point slope form. As y minus y0 equals m times x minus x0. We just need to plug in m equals -4/3 x0. Well, what was the point x0 comma y0? Right, it was 1 comma 5. So we plug in 1 for x0 and 5 for y0. So that'll give me y minus 5 equals -4/3 times x minus 1. You can distribute the -4/3 if you want. You could write this as y minus 5 equals -4/3 x. That's multiplying this. And then you also have to multiply that. So negative times a negative would make a positive, so we'll have plus 4/3. And then if you really want to put it into y equals mx plus b, you can add the 5 over. And then we have to add these two fractions together. 4/3 has denominator 3. So to add these two numbers, I need to write 5 as a ratio with denominator 3. 5 is the same as 15/3. So off to the side, maybe you can say 4/3 plus 5 is the same as 4/3 plus 15/3 is the same as 19/3. So this would say y equals -4/3 x plus 19/3. So this is the y equals mx plus b form. I would be perfectly happy with this as an answer on a test if I just asked you for the equation of the line. And you'll be doing a lot of this in the current homework sets. All right, this is all we have time for today. I do appreciate you guys for hanging out these extra 5 minutes. If you have trouble with any of the homework problems, please don't hesitate to come by office hours. I have an office hour right after this from 11 to 12. Or you can email me or send me a message on Canvas. The best way to get useful information from a Canvas message or email is to take a photo of your work and attach that to your message. That way I can look at what you're doing. But we have covered everything that you guys need to get through the homework. So please do try to get all of the homework and quiz knocked out by next Tuesday. As always, though, if you need more time, just let me know. If you have trouble finishing something up and you just want a few extra days to work on it, you can send me an email or Canvas message. Just tell me which assignment you need extended and how long you'd like it extended for. Any questions before we sign up for the day? Zoom out so you can see the end of that. Okay. Let me check the chat here just in case. There's something new. Why isn't this showing up? Oh, neat question. Yeah, if we wanted to put that into standard form, we certainly could. We multiply both sides by 3, and then we would have 3y plus 4x equals 19. Yeah, very good. Yep, I think that's exactly correct. Alrighty then, I'm going to go ahead and sign out. If you do run into any questions while you're working on the homework, or if you have any problems with anything really between now and Tuesday, either come by an office hour, they're all posted up in Canvas there, or send me a message on Canvas or an email. Canvas messages are best because they are automatically filtered by class. But that is it. I'll see you guys next Tuesday. Please finish the homework. Take care. Have a good weekend.